Welcome back. Today we will start with the shorted compact variations of circular microstrip antenna as well as equilateral triangular microstrip antenna. Yesterday we introduced these concepts of edge center shorted patch as well as the corner shorted patch, which are shown over here. Similar designs, similar configurations will be dealt with the designs of circular patch as well as equilateral triangular patch. Now before going further, I will just explain the design procedure to realize these two configurations as per the given frequency. So now we will take up one design example. So here our job is to design a edge center shorted microstrip antenna for the given resonant frequency, where we are supposed to find out the dimensions of the patch. Okay, we need to find out the patch dimensions for this frequency for a given substrate thickness. So what is given to us is the frequency and the substrate parameters. Okay, these parameters are given to us. We need to find out what is L and W. The procedure is bit of approximation in the sense that important parameter such as epsilon R is not known. Everyone knows that effective dielectric constant depends upon the patch area, or to be very precise, the length and the width of the actual patch. These are unknown to start with. Plus, we don't know exactly the fringing field extensions which will take place where it will give you the calculation of effective length and the effective width of the patch. Because everyone knows there will be the field variation is starting from here, so that naturally the field is 0 over here, and field are positive in this thing and they are varying quarter wavelength. So there will be a fringing field presence all across the patch perimeter. So we need to find out what are the effective dimensions. So these things are not known to start with, which are actually dependent on these things. So we will do a bit of approximation here, and that approximation fairly gives me the dimensions of the patch at a given frequency. So what we will do, everyone knows that FR here is C upon 4 effective resonant length under root epsilon RE. Okay, effective resonant length upon epsilon RE. Now what is LE? LE is the resonant length, which is actually LE plus WE by 2. Okay, this LE is not same as this. I will just mark this as a different variable, effective resonant length LER. So this is your resonant length. So what we will do, I approximate this to L plus W by 2. This approximation holds good for thinner substrate. How much thinner? Generally it should be less than 0.02 lambda G. Okay, when you are designing your antenna on a thinner substrate, definitely this approximation holds good. For a thicker substrate, when you are designing a shorted patch, definitely there will be slight variation, but still this procedure gives me a fair bit of closeness with respect to the actual dimensions calculated for the given frequency. So it is not that this procedure will give you a way off result with respect to the calculated frequency. So to start with, what I will do, I will approximate epsilon R to be epsilon R itself, RE to be epsilon R. Okay, then LER will be L plus W by 2. That's what I will assume, and then I will calculate LER using this formula. This formula I will use. So this will give me LER. Now, once the resonant length is known, there are two ways you can look at the problem. What you can do, either you can consider this to be a square patch, because there are no such constraints in designing the shorted microstrip antenna. Since it's a compact variation, there are no hard and fast rule that L and W should have some proportion or it should be a rectangular dimension. So I can assume to be a square patch as well. So I can assume this equality, or I can assume some equality where L and W may hold some ratio. Again, this is totally a designer choice. So I am assuming one of these two approximation, I will select with one of these two. So LER is effectively 3 LE by 2, and from this I calculate the length of the patch for a given frequency. So this is how I design a center shorted rectangular microstrip antenna at a given frequency. Now the next point comes with respect to the impedance matching, because ultimately you need to feed the antenna where you will feed. As we have seen in the last lecture, in the shorted design, the impedance variation increases. In fact, the polarity which I have shown over here, the positive means it's a positive field strength. Now if we really judge the magnitude of that with respect to the conventional microstrip antenna without any shorting post, that magnitude is much higher. Just to give you a fair bit of idea, if the edge impedance for a conventional rectangular microstrip antenna on FR4 substrate is somewhere around 250 ohm, that may be as high as 1000 ohm for a edge center shorted rectangular microstrip antenna. So that kind of variation in the impedance takes place going from shorted to the open circuit edge, where the quarter wavelength variation is shown. So then I need to put this feed point as close to the shorting post as possible to realize a 50 ohm matching, 50 to 60 ohm matching. So generally what we do, we keep the shorting post as close, maybe 3-4 mm spacing from your shorting post, where you probably get a 50 or 60 ohm impedance matching. So this is how you do. But again, as I mentioned 3-4 mm, it is also a function of tan delta, because tan delta is the loss tangent of the substrate. If the tan delta value is very small, then that 3-4 mm may just be 2 mm also, because if I design this antenna on RT toroid substrate, my feed point has to be very close to the shorted point, whereas if I design this antenna on FR4 substrate, that feed point location may be 4 or 5 mm from the shorting post. So again, these design procedures may slightly differ, the selection of the parameter may slightly differ depending upon which substrate we are using for finally designing your rectangular patch. Okay, so this is all about realization of shorted, edge center shorted rectangular microstrip antenna. Now the next point I will go upon, I will put a shorting post over here. Okay, I will put a shorting post over here. The procedure remains the same. The only difference what will happen is this now W by 2 will be equal to W. Why? Because from this point till this point it is lambda by 4. Okay, from the one corner to the other corner it is lambda by 4. Now one can ask a question, why exactly these lengths are considered? Actually these lengths are considered by looking at the surface current distribution. You can actually simulate this in any of the simulation software, and you will see that predominantly the surface currents are varying like this. Okay, and the dominant effect is shown by this surface current in deciding the quarter wavelength. Okay, so let it be a corner shorted, this length decides your resonant length, whereas in edge center this length decides your resonant length, and that's why these lengths are taken. They are not just randomly or arbitrarily taken. By looking at the current distribution behavior at a given frequency, these lengths are being finalized. Okay, so now going to the design of corner shorted rectangular microstrip antenna, what we will do, this length equals lambda by 4. So I will equate LER is equal to L plus W. That is the only modification which you will take while designing a corner shorted microstrip antenna, and then one of these two approximation. Now remember, this 0.8 can be a number as per your design procedure. You may have a wider rectangular patch, okay, where this is L, this is W, or you may have a patch like this where L is more than W. So this is totally as per your design requirements. What I mean by design requirement means the size available to put your shorted design in your application area. So if I am having a narrow patch which is allowable by as per my practical application, I will select this design. If I am allowable with the wider patch, I will take this design. Remember, the gain relation which is existing in between the conventional rectangular microstrip antenna does not really hold here with respect to the shorted design. So gain relation has no effect in deciding these two parameters predominantly. It has a major effect in case of conventional rectangular microstrip antenna. Okay, so by just replacing LER with this equation, I will calculate what is the resonant dimension at the corner shorted microstrip antenna, and I will calculate their patch dimensions on a given substrate thickness. Again, selection of feed point location, it should be as close as possible to the corner position. and this value whatever I have mentioned may vary depending upon your substrate selection. Remember, for a lossy substrate it may be at 5 to 6 mm or maybe 4 mm from the shorted point, but for a non-lossy substrate like RT-Deroid or Arlong, it will be as close as possible to the shorted point. Okay, so this is how the two antennas are designed. Now looking at the comparison purpose, remember the bandwidth and the gain more or less same in both the designs. Okay, radiation pattern is also broadside with larger contribution in the conical direction as I have explained in the earlier lecture. The only difference is in this case, in case of edge center shorted design, okay, in case of edge center shorted design, the E field, effective E field are horizontal. Okay, why? Because the field is varying like this. Whereas in corner shorted design, the effective field are along the diagonal. Why? Because the fields or the currents are varying along patch length as well as width. So, with respect to the planes of radiation, E plane in edge center shorted microstrip antenna is aligned at phi equal to 0 degree. That is horizontal x-axis. Okay, if I consider this as x-axis. Whereas in case of corner shorted microstrip antenna, if this is my horizontal x-axis, then along phi equal to 45 degree, my E plane will reside. That is the only difference. Otherwise, there is absolutely no difference in the case of corner shorted microstrip antenna against edge center shorted. Okay. Only thing what you need to do, once your patch is kept horizontal, in case of edge center shorted, you need to keep it at angle or you need to rotate this like this so that your alignment is not affected. That is the only difference between the two. Yes, with respect to corner shorted, you get larger reduction in the frequency because as against W by 2, you have W in calculating the resonant length or the patch dimensions. Okay, so here we complete the design procedure for calculating the patch dimensions for the corner shorted rectangular microstrip antenna. So here you can just take up one design problem, that design, I'll just put it in a different color so it will be more highlighted. Design on edge center shorted as well as corner shorted microstrip antenna for a frequency of say 1 GHz on RT-Deroid substrate. Epsilon R is 2.33, H is 0.16 centimeter. So design a corner shorted and edge center shorted rectangular microstrip antenna around a given frequency. Now, and next part is compare. Compare that with respect to the dimensions of the equivalent RMSA at that frequency and calculate about the area reduction. Talk about the area reduction. Now, first step is follow this procedure and evaluate what is L and W. What is L and W over here by following this procedure. So calculate L and W. Next part is something very important, to estimate how much reduction in the area which you have obtained with respect to the conventional rectangular microstrip antenna design. So that part now I will explain. I will presume that you have calculated these dimensions and now we will go to the calculation of area reduction which we will obtain using this. Okay. Okay, so now I have calculated area for edge center shorted microstrip antenna. Suppose it comes out to be say AX. Then I calculate the area for corner shorted microstrip antenna. Suppose it is AY. Okay, area means what? It is basically L cross W. After following those design guidelines, you must have calculated those areas. So area is L cross W in both the cases. AX, AY just represents two separate designs. Now how to calculate the area reduction? What we will do at that frequency using design procedure for conventional RMSA operating at TM10 mode at 1 GHz, you find out what is L and W. Okay. Next step here is using design procedure of conventional RMSA. Okay. Find out the dimensions of the patch which works at TM10 mode. Which works at TM10 mode. So you calculate that dimension. Okay. So that dimension say A conventional. Okay. That dimensions are say A conventional. Now we will talk about the area reduction. Naturally, this A conventional will be much higher in value. Okay. So now with respect to the edge center shorted design, okay, area reduction is basically A conventional minus AX upon A conventional. Why? Because with respect to the conventional I am calculating the area reduction. Into 100 will be your percentage area reduction for the given configuration against the conventional antenna. This is how you calculate your conventional area. Now with respect to corner shorted design, just replace AY by AX. Okay, just replace AY by AX. You will calculate the area reduction in the conventional in the corner shorted microstrip antenna against the conventional design. And remember, these reductions you will observe yourself that these reductions are more than 90% in nature. More than 90% in nature. These are the reductions which you obtain in your edge center shorted microstrip antenna as well as corner shorted microstrip antenna. Okay, so that actually reflects upon the compactness in the design. How much compact are these configuration with respect to given frequency against the area. So here we complete your calculation and the design procedure for edge center shorted microstrip antenna, corner shorted microstrip antenna as well as their equivalence and the area reduction with respect to your conventional design. Okay, now we will go to the designs of CMSA and ETMSA, the compact variation, as well as we will touch upon how the compact variation of CMSA, ETMSAs are designed. Okay, so here we have already completed this. Okay, now these are the compact variations of CMSA. Now here, this is your CMSA operating at fundamental TM11 mode. So if you see, this variation is half wavelength variation along the diameter as well as along the perimeter. Yesterday we have seen a compact design of CMSA where we took the symmetry of the configuration and we realized the SCMSA, semicircular microstrip antenna. In that configuration we just have used the symmetry and we obtained a 50% area reduction. No shorting was used. Now what we will do, another semicircular antenna we will derive but by using a shorting technique. But here the positioning of the patch where the shorting post is placed has to be decided carefully. You will observe that in the center line, not vertical line, not the horizontal, because along the horizontal there lies a symmetry, but along the vertical line the field is 0. Okay, just where this procedure is something similar to your rectangular microstrip antenna design. Okay, so in the center the field is 0. So what I will do, I will put series of shorting posts and remove half of the part. That will lead to a shorted semicircular microstrip antenna. Okay, in fact this design we have already discussed, so I will not discuss this into details. Okay, so this we have gone over here by using a shorting post and a semicircular patch was obtained. Now the further, so here in this design or in this design we obtained 50% area reduction. Okay, similarly the last super compact design of the circular microstrip antenna is a shorted 90-degree sectoral microstrip antenna. How it is realized? You can come to this configuration from here as well as here. I will talk with respect to the semicircular patch. Semicircular patch we obtained by only considering the half of the design. Now what we will do, in the semicircular patch at the fundamental mode, the same field distribution is present. Means what? At TM11 mode, this edge is positive, 0 and negative. And from positive to 0 to negative, you have a half wavelength variation. Okay, because it is something half of this, so this top half remains over here. Now what I will do, in the center line, very similar to this, there exists a null field point. There exists a null field point. So what I will do, I will put a series of shorting posts along this axis, and that lead to the, and remove half of the part, and that will lead to the design of shorted 90-degree sectoral microstrip antenna. How much area reduction with respect to CMSA? 75%. Because 75% of the patch is removed. Frequency of the resonance nearly remains the same. Maybe it will vary by 40-50 megahertz depending upon the substrate parameters. Okay, but nearly the frequency remains the same. 75% reduction in the area is achieved. Okay, so from here to here also I can go in the same manner. Here what is the field distribution? It is 0 to positive. Again positive to 0. So with respect to this coaxial axis, there exists a symmetry of the field. And since in the circular patch radius decide the resonance frequency, I can apply a same equivalence of realizing a semicircular patch over here in shorted semicircular patch, that will lead to the design of shorted 90-degree sectoral microstrip antenna. So shorted 90-degree sectoral microstrip antenna is the most compact variation of your circular patch, where 75% reduction in the patch area is obtained. Now further reduction in these, any of these, rather these as well as these configurations can be obtained by changing this shorting ratio, shorting width ratio. What we have seen it in the case of rectangular microstrip antenna, that shorting width WS which we have mentioned earlier. Okay, that WS parameter which we mentioned yesterday, this parameter, I can apply the same parameter over here also. I can say I can use a partial shorting here also, and I can change that shorting width and realize a further reduction in the frequency for the given patch size. So similar design can lead to a edge center shorted 90-degree sectoral microstrip antenna, or a edge center shorted 180-degree or semicircular sectoral microstrip antenna. So similar designs are possible. Okay. I will take up further compact configurations after I discuss similar variations with ET-MSA. Okay. Now these are the compact variations of equilateral triangular microstrip antenna. Now equilateral triangular microstrip antenna, as we know, all the angles are 60 degree in nature. So in equilateral triangular patch, null field line lies along 1/3 of the patch geometry. Null field line is lying along 1/3 of the patch geometry. So first thing, I will use a shorting post which are placed all along this null field line, and I can use either of the shorted part. Okay, I can use either of the shorted patch. So this will lead to a shorted 60 degree half equilateral triangular microstrip antenna. Why 60? Because this angle is 60. Or this will lead to a complement of half equilateral triangular microstrip antenna, where only the bottom half is used. Okay. Other way is apply the symmetry of the field distribution. Apply the symmetry of the field distribution. So I will use a symmetry along this coaxial line and use only half part. So it will lead to the design of half equilateral triangular microstrip antenna, which we have seen in the earlier lectures, where 50% reduction is possible. Next step in that, you put shorting post along the null field line over here and use either of the two. That will lead to a shorted 30-degree sectoral microstrip antenna, which is present over here, or complementary of that, which is shown in the following figure. Remember, in all the cases, you are realizing the compactness, you are realizing the size reduction, but at the cost of bandwidth, gain, and the radiation pattern. Okay, generally the gain reduces, bandwidth also reduces, and hence the radiation pattern becomes higher cross polar in nature. Now, before going to the further designs, I will just touch upon and give brief design details about a single shorted compact variations of circular as well as half equilateral triangular microstrip antenna. Okay, so we'll just touch upon that part towards the end of this lecture. Okay. See, this is your conventional circular microstrip antenna and this is your equilateral triangular microstrip antenna. By looking at the field distributions, we have seen their compact variations. Now I will talk about their compact variations with respect to single shorting post loaded design, because ultimately they are the most compact configuration using a single shorting post. So what I will do, I will put a single shorting post over here and feed over here, or I will put a single shorting post over here and a feed over here. Now in this case, what is the resonant length? The resonant length is obviously this one. The field is 0 at this point and the field is positive towards this point. Now what is the resonant length here? LER, resonant length. It is basically half of the patch perimeter. What is the perimeter of the circle? It is basically 2 pi r. Okay, so the resonant length is pi re. Okay, resonant length is pi re. So the frequency which is calculated is C upon 4 into LER under root epsilon r. So this is how you calculate a resonant length of resonant frequency of the single shorted circular microstrip antenna using this equation. So I can ask you, design a single shorted circular microstrip antenna for a frequency of 1 gigahertz for RT derivative substrate, the parameters which are given. The procedure lies like this. You can assume epsilon r to be epsilon re only, and then using this equation and this equation, you first find out what is LER used for the given frequency and then find out R for the given LER. And that's how you complete the design of single shorting post loaded circular microstrip antenna for the given frequency. Okay, it is as simple as that. Same procedure we need to apply, only the equation of RE differs, which is basically half of your circular patch perimeter. Now, going to the equilateral triangular design, here once you put a shorting post over here, remember this is your patch side length. So patch side length is now lambda by 4 in length, or it is basically your resonant length. Now here, resonance frequency equation of ET-MSA we are not referring. Okay, resonance frequency equation of ET-MSA we are not referring. We will refer, since it is a quarter wavelength resonator, I will use this equation only. I will use this equation only to calculate the resonance frequency for a shorted equilateral triangular microstrip antenna. So if I ask you, design a shorted equilateral triangular microstrip antenna at 1 gigahertz on RT derivative substrate, the first step is calculate what is S using this equation. Epsilon r you can assume to be epsilon r to start with. There will be slight error introduced, but still it gives me a fair bit of approximation with respect to the simulated as well as the measured value. So here calculate S for the given frequency, and once you calculate S, that is basically your shorted length or resonant length. From that you can design a equilateral triangular structure. Okay, remember here I have not used the resonance frequency equation for the equilateral triangular patch, and since it is a shorted patch, it is a quarter wavelength resonator. I am using that quarter wavelength resonator here only. Okay, so these are the two super compact variations of circular as well as equilateral triangular microstrip antenna where a single shorting post is used. Okay, so you can be asked with a question that design these variations for the given frequency, where these equations and the design procedures are to be followed. Okay, so now just to summarize, here shorted microstrip antennas, they are quarter wave in length. Okay, feed point for any design have to be placed very close to your shorting post. Otherwise, you will not get an impedance matching. Next point is, it offers 50% patch reduction, size reduction by using the symmetry or the shorting post, as we have seen it in the circular design as well as equilateral triangular design. Okay, but still further reduction in the frequency is possible by changing that shorting edge ratio WS, which you have mentioned in the rectangular patch. Next, shorted antenna definitely offers much smaller bandwidth. Okay, maybe 50% or less than that with respect to the conventional rectangular microstrip antenna or conventional half wavelength microstrip antenna. And since they have a asymmetrical field distribution around the patch periphery, it gives me a higher cross polar radiation pattern, or maybe the broadside level will be 3 to 4 dB down with respect to the end fire level, as we have seen it in the earlier lecture for a rectangular microstrip antenna using a shorting post. Okay, but yes, it gives me a fantastic reduction in the patch size. And remember, higher cross polar is not really a disadvantage, because in the case of multipath propagation environment where you need to transmit a signal over a short distance, even if the gain is small, but because of the high cross polar nature of the radiation as well as the antenna can receive signal from the end fire direction, your antenna, shorted antenna, can find a best application in any of the wireless application where you need to receive the signal from all possible directions, of course over a small restricted range. So definitely the disadvantage can be made as an advantage here for the shorted microstrip antenna variations with respect to their gain and radiation pattern. Okay. Next point is related to the slot cut designs. Of course, those designs in detail now we will cover in the next lecture. Thank you.